Okay, so we're looking at question 3 here, and it's asking for a tight asymptotic bound for this function as a function of n and m. So let's just look at the parameters. We have n and m. We terminate when n equals 0. And it seems like these lines just pretty much creates a variable k that is incremented by m+1 recursive calls to many n. So it looks like at each layer, at each recursive call, we can't get around this. We have to do O of m. We have O of m runtime for each recursive call because we have this for loop that loops from 0 to m, and there's no other way around it. And let's look at the branching factor next. So the branching factor here is pretty much asking you, like, from one recursive call, how many recursive calls do you make, right? We can see that we have this for loop, and we have m recursive calls because we call many n m times inside this for loop. So this means that we have m+1 technically, but should be fine to say it's m recursive calls. So at the branching factor is m. And then the final step is to look at how many levels are there in this tree from root to leaf, right? So let's look at n. N is important here. So we have n equals 0 to be terminating condition. And at each recursive call, we decrement n by 1. So the root has n equals to n. And then the next level, the next level has n minus 1. And the next level has n minus 2. So when is this 0? It's when we're at level n. So this implies that our tree is of height n. Okay, now let's look at the runtime for each layer. So we know that each recursive call is O of m, and the branching factor is m. So this first layer has only one recursive call, so just one call. So we have over m time. Here we can see that we have m nodes, each doing over m time. So this takes m squared. The third row has m times m by the branching factor. So we have m cubed total time. And finally, similarly, at the last level, we have m to the n runtime because we've branched out m to the n times. So we technically have O of m to the n+1, but asymptotically, that's the same as m to the n. So let's just add all of these up. And we know as m approaches infinity and n approaches infinity, all of these small fry are pretty irrelevant when you look at the final one. So your final runtime should be O of m to the n. And this is this works this way because we can see that m is never changed. So our branching factor is constant throughout our entire tree. If this branching factor is different, then this problem will be slightly trickier. But in this case, we can see that the branching factor is the same. So we can create this summation and kind of in the end just realize that the last one is the biggest one, outpaces everything else. So our total runtime is of m to the n. And this is the best and worst case runtime because there's like no other way around having to branch out m times and do O of m operations for both, for each recursive call. Okay, now let's look at the next one. So skip. So this question is, let's do it a similar way. So at each level, our runtime seems to be just constant, right? We don't have any loops. We only check if n is less than or equal to 1 or not. And if it isn't, then all we do is to make 2 recursive calls. So we're doing 3 operations. We can see skip n over n is just skip 1. And pretty much that doesn't do anything. So our tree kind of looks like this. So we have this, and then we have this, and then we have this, and so on and so forth. And these nodes are only constant time operations because we just immediately terminate here. So we can kind of just ignore them. And so all we really need to do is look at the height of the total tree, pretty much, as we can see, right? So our branching factor is pretty much 1, because again, we just these branches just have constant runtime. We just pretty much ignore them, and they don't also branch out themselves. That's why we can ignore them. If they branch out themselves, then you'd have to keep them into consideration. But since they don't branch out, you don't really need to worry about them. The height, right? So let's look at how many. Let's look at the behavior n, right? So initially n equals to n. I'll just say, okay, I'll just say little n to differentiate. And then the next step, we see here we divided n by 2, so n equals to n over 2. And then here we divided n over n again, so this is n equals n over 4, and n over 8, and so on. So we can see that whenever n is less than or equal to 1, we just terminate. So how many branches do we have? Or sorry, how many levels do we have? We can see that we have log of n levels because we're dividing by 2 at each level, and we stop when n is 0 or 1, pretty much, less than or equal to 1. And that gives us a runtime of log n. And this is also the best and worst case runtime. There's no way to kind of short circuit your way out of this. You have to call skip n over 2 if n is greater than 1. You can't really just not do that step. So cool.